All right, let's get started. Okay, PS, is it 10 now? PS 10 is out and due at the end of the week. Any issues, problems, questions? Yes? Say what?
I just clicked on the link for LP Solve and I tried to set up an environment for using it, and I just kind of felt like I was going down a rabbit hole. So I'm just wondering what your recommendation for using it is.
Well, I installed it most recently a year ago, so I don't have recent memory of it. Has anyone else installed LP Solve? Had any trouble? Or anyone installed LP Solve? What kind of machine? Yeah, I'm afraid I don't have any particular advice. I just installed like you'd expect when I did it. There are other options though. You can probably find it. Yeah, I'm sure you can find different LP softwares. Any other questions? Yes?
My guys, I got the example building, passing the first test. Is there any recommendations
Okay, I didn't hear the last bit.
So I passed all the examples and 8 times, but I'm getting the wrong answer for later tests. So I'm just wondering if there's any, pointers and stuff that I might look for.
I guess be careful about, there's the issue of if you close the left room of the two, in the next row you can't close the right one. Be sure you've got that, you're dealing with that right. Because I know I was looking at a solution yesterday to get confused about it. Just make sure you didn't miss a small detail there. Any other questions? Okay. I want to just make a few final comments about dynamic programming, and then we'll return to linear programming. Now, I've mentioned all along that when you're doing dynamic programming, when you come up with a recursive solution and you find that it's too slow, but that you can speed it up using dynamic programming techniques, you've got two choices. You can either memoize a recursive solution. In other words, create a cache and look for when you enter the method, the recursive method, see if you've already computed that answer, so just return it. Otherwise, at the end, after you compute the answer, you save it. That's one option. And the other is to, instead of keeping the recursive solution, sort of view the recursive solution as instructions for how to fill out an array iteratively, and then fill it out. And don't do recursion at all. What are the trade-offs? Why would you choose one over the other? Why would you choose do it using caching as opposed to creating a table, filling it out? Yeah.
In some situations, the recursive one can avoid extra calculations.
Okay.
The table has better locality.
So there are some situations where if you fill out a table, you'll compute way more subproblems than really need to be computed. The recursive solution sort of is optimal in that sense. It only computes the subproblems that have to be solved. The other thing he said was that the table has more locality in terms of, I guess in terms of the memory and the caching and such is what you mean. Okay, that's one trade-off. What else? Yeah?
Can memory be a trade-off? Because with recursion, you'd have a higher stack trace.
Okay, so if you do recursion, you can you're using stack frames, using stack, and if you're not careful, you can run out of stack space, depending on where your limit is set. And just typically an array, using an array to fill in the solutions is going to be more memory efficient than using a hash table. Okay? Those are the only trade-offs? Yeah? Okay? That's the important one in my mind. Doing it recursively is just flat out easier. You've already got a recursive solution, and just by memoizing it, you speed it up, and you don't have to worry about doing something different to fill in a table. If you create a table, you've got to worry about in what order do I fill in the boxes in the table. Whereas with the recursive solution, it's not consideration. So there are, people, hardcore programming contest folks that do dynamic programming seem to reflexively go right to filling out a table just because they're really used to dynamic programming. But when you're getting started at it, memoizing is, in my mind, the way to go unless you got a good reason not to. So we said that memoizing is usually easier. If it's, if you've got a problem where you figure that every subproblem is going to have to be eventually solved, tables will be faster, can be slightly faster than the recursive version. On the other hand, if only a small number of subproblems have to be solved, memoization will win out. We'll see an example of that. And you got to be careful when you're using the recursive solution not to blow the stack. Now we've looked at these examples in lecture, and you've looked at some on Caddis. And I'm going to go back at some of these examples and just try to evaluate whether we should memoize or use a table in different situations. So here's the rod profit, the recursive solution to the rod profit method. And this is an example where all subproblems must be solved. If you want to know what's the best you can do with some length of rod, you've got to consider all possible ways of cutting it up to find the best solution. So in that case, you can squeeze some more performance out by using a table instead of by using recursion. So what would it take to turn this into something that fills in a table? We know how to memorize it, but what would it take to fill in a table? Because the way to think about that is, if you add a cache to this, it's basically a table, except it's sort of being filled out dynamically in whatever order the method discovers. Typically for if you're going to use the table version, you create an array and write the elements into the array. So what would it look like? So you'll notice this is the rod profit method. We're iterating through all possible piece lengths. For each piece length, we are looking up the value of that piece, plus we're computing what we can do with the rest of the rod recursively. So there's our recursive call. We compute the max over all possible piece lengths and then return it. So where would a table show up in here? Yeah.
Where you compute profit?
Okay. So right here, instead of recursively computing the profit, what would you do? Well, we'd store it elsewhere. Okay? How does the recursion disappear when you have a table-driven method? Yeah?
Don't you fill in the table first and then?
No, we fill in the table as we compute. Yeah?
That's going to be a lookup to the previous entry in the table.
So this would be where you look up in the table. So instead of making a recursive call to find out the best you can do with the remaining piece of rod, you just look up the answer in the table. Now, where would you store things into the table? Yeah.
Where you return it.
Right. Stored by caching. Before you return it, you store it into the table. So you call the method. It iterates through, figuring out the best you can do with each rod length, looking up answers to subproblems in the table as it goes, and then when it's done, it returns the max profit. So that implies that you got to be careful of the order in which you compute things. You got to make sure you don't try to compute the answer for a certain rod length before you've computed the answer for all shorter rod lengths, where you'd be trying to look something in the table, look up something in the table that's not there yet. At the recursion, it doesn't matter because if it's not there, you go and compute it. So And this is what it turns into. It's no longer a recursive method. We declare a table to hold our profits. So this table is going to contain, for every given length of a rod, the maximum profit you can make with that rod. And then we just consider all rods. We end up with a doubly nested loop here. We consider all rods from length 0 up to the maximum length. And we figure out the best we can do with that piece. So we figure out the best we can do with a rod of length 0, and then a rod of length 1, and then a rod of length 2, and a rod of length 3. That way, when we get into the inner loop here, and we go to look up rod length minus piece length, why are we guaranteed the answer will be in here? Why are we guaranteed that when we look up the profit for some leftover piece of rod, that we've previously computed the profit for that length of rod? Yeah.
Do we start at the smallest rod?
Right. We solve the problem for rods of length 0. And there are no subproblems of that, so we'll just store that number right into the array when we're done. Then we compute the profits for rods of length 1. And that depends on the profit for a rod of length 0, which is previously computed. Eventually we compute for rods of length 10. Now it depends on the profit you can get for rods of length 9, 8, 7, 6, 5, 4, and so on. But since we're iterating from 0 up, we previously computed those. Now, if you're a little bit confused and you ran this in the other order, what would happen? Or if you started the rod length at n and went down to 0? What's that? Right. We were in this inner loop and we're trying to deal with a rod length 30, and we've got to find out what's the best we can do with a rod length 29. We try to look it up. It wouldn't be there. So this is why I say there's a little bit of intellectual overhead with filling in the table. You got to make sure you fill it in the right order. In this case, it's pretty easy. Sometimes I've seen problems where you've got to start in one corner and sort of work diagonally to the middle of the table. And that's a little hard to get your head around. Yeah.
Wouldn't this call an exception though, starting from rod length 0, calling from profits at a -1 point?
Well, how would it do that? If we call it the rod of length 0, for rod of length 0, max profit is 0, it would then right here,
Yeah.
piece length would be 0, but piece length is not good, so the loop ends immediately.
Okay, yes.
And then we store 0 as our max profit, and we go to 1. And after 1, we would look up profits of 0, which is previously computed. So each time through this loop, we got one more element in our profits array. Just in time for them to be looked up in the next iteration. And then when we're all done, we find our answer at the end of the array. So it's really just turns into a doubly nested loop, no recursion. Okay. Any other questions about that? Now, the advantage of the recursive method of caching is you don't have to think about that, right? You just put the cache on and do it. All right, here's an example. This was the knapsack problem without repetition. And you'll recall the definition for it was that, say this box right here in the upper right-hand corner, for the particular example we looked at, the number you put there depended on the number right below it in this cache and the number in the row below it that 7 hops over. And what I've highlighted here, again, I don't have the example we were solving here. There were 3 things to choose from. If you're trying to compute the best you can do with a knapsack that holds 11 pounds, the yellow boxes represent the only subproblems that matter. Right? You could compute what goes here at 10.3, but the number that you write there is not going to be used to compute the number at 11.3. It doesn't matter. So if you fill this in as a table, you would have to fill it in starting from the left. You fill in this row, and then you fill in this row, and this row, and you end up with the right answer there, and you have a table full of numbers. But most of those numbers are useless. Only the ones stored in the yellow boxes contribute to the final solution. So if you did this by table, you do a tremendous amount of work. But what happens if you do it recursively? You just recursively start it off, say, okay, compute what goes in that box. Yeah.
If you had this solve multiple, like let's say first you were doing, well, what am I trying to say? If you did the recursive one multiple times,
True.
then you could be recalculating a lot. Whereas if you have the
Mhm.
table, you can just look everything up.
So if you were trying to find a solution for this box and then later for that box and later for this box, if you reuse the cache, if the items and their weights and their values haven't changed, then yeah, you could reuse the table and there'd be some value to filling it all in. But what if you're just interested in the one answer? Iteratively, the complexity is the number of the capacity of the pack times the number of items. But recursively, the only recursive calls we would make would be to the yellow boxes. So we do far less work in that case. So the recursive method wins out. Now suppose we could be, I don't know, maybe you could be really clever and figure out as you're iterating which boxes really matter. That seems kind of hard. I think you could actually with some modular arithmetic, but why bother? Just do it recursively. Okay, this is something that was actually an issue for some of you on Caddis, although I only heard from people using Python that had this problem, that ran out of stack on last week's Caddis problem. So this is the purely recursive method. Okay, and you could wrap, you could imagine wrapping a cache. You could cache it. But look at the order in which we're doing. We're starting with a piece length of n. So let's say n is 30 initially. We start with 30, then we look at 29 and 28 and 27. Okay. So compare that with if we turn the loop around. So instead we start with a piece length of 1 and then work up. Which is better from the standpoint of, which is better from the standpoint of using of the runtime stack? How deep can the recursion go in this case? Okay. Can it go in deep? Can you get n stack frames on the stack in this case? Okay, how would that happen?
30, 29.
Well, let's see. We start out with 30, and then the recursive call we're going to make is to compute rod profit of what? What will the first recursive call be? Imagine n is 30, so piece length starts out at 30, and then it gets counted down 29, 28, 27. So when piece length is 30, what recursive call do we make? 0. Okay? So how deep did the recursion go? Through 2 stack frames on the stack, right? One where piece length was 30, and then one where piece length was 0. And now 0 is solved in cache. Now piece length becomes 29. Oh, let me back up. Yeah. Okay, now piece length becomes 29. What recursive call do we make? Right? N is still 30, piece length is 29, so we're calling for 1, right? So how many levels deep in recursion do we get? We get where piece length is 30, then piece length is 1, then that's going to make a recursive call where piece length is 0, so we got 3 deep. Okay, what happens with piece length is 28? Okay, piece length is 28, what's the recursive call going to be? Piece length of 2, then what? Piece length of 1, but that's already cached. Piece length of 1 is already cached, so we only went 3 deep. Okay, what's going to happen to piece length of 27? We'll have a frame for piece length of 27, Then it'll make a call to raw profit where piece length is 3. That'll call piece length of 2, but 2's already cached, so we only got 3 deep. We're never going to get more than 3 levels deep in recursion. Now, what happens when we go the other direction? What's going to happen the first time if piece length is 1? What's the first recursive call value? No, so n is 30, piece length is 1, so our recursive call is going to be what? 29. Okay? So we make a recursive call to 29. Now n is 29, piece length is, we start the loop here, piece length is 1, so how, what's that called? 28, 27, 26. So the first time we go 30 deep in the stack, compute piece length of 0. At that point, every solution is cached. And after that point, recursion bottoms out after 1 recursive call. But the point is, previous slide, we never went more than 3 deep before we found a cached answer. Here, the first time, we go 30 deep. So maybe that's not a big deal, but what if we're trying to compute piece length of 10,000? This way, first recursive call goes 10,000 stack frames deep. The other way, 3 deep. Doesn't matter how big n is. So when people ask me on Piazza about their Python solution below in the stack, when for the caddis problem, the answer I gave was turn your loop around the other way. Unfortunately, other people gave the answer increase your stack size, which works, but isn't the lesson I was trying to get across. All right? So conceptually, it doesn't matter in which order you do. This is just saying you've got something of length n. Try all possible ways of cutting it up. Mathematically, it doesn't matter if you consider them in the order. Okay, cut off a piece of length 1, then 2, then 3, then 4, then 5, or whether you say, okay, cut off a piece of length 29, then 28, then 27, then 26. But the order that you choose can have a dramatic effect on how much memory you need. Essentially, you want to use an order that's going to tend to solve the simpler problems first and get them cached so that they're cached when you go to compute the more complex problems. And it won't affect the asymptotic complexity of the running time, but it will can affect the depth of the stack, the space consumed. So that's an issue that you need to be aware of when you are memoizing. There's one last problem I'm going to skip over. So anyway, that's what we have to say about dynamic programming. And currently you're working on a dynamic programming problem. There's going to be one more next week involving Spider-Man. And what's going to make it a different kind of problem is you're not just going to find the optimal answer. You're going to have to recover the solution from the cache, which is something you haven't been asked to do yet. Okay, let's return to linear programming. Okay, this is where we were at the end of class last time. So let's just sort of remember what we were looking at. We talked about linear programming. And first of all, what is a linear program? Yeah.
A program that relies on the number of, I guess you would say like input for its program.
Okay. I guess that's a very high level description of a linear program, but more specifically, yeah.
Just has a bunch of linear constraints and we're trying to maximize or minimize some votes.
All right. So you have some variables, and you have linear constraints that constrain the values of the variables. In this case, we got a whole pile of constraints. Okay, that's one thing. Linear constraints on the values of the variables over possible values of the variables. And then, what's the other thing? Yeah.
A linear
Right, a linear objective function. So it's going to be like sum and difference of variables in, possibly with coefficients that you're either trying to maximize or minimize. So what we're saying linear programming is I've got all these variables. These are the constraints on the values. What's the largest I can make the objective, which in this case is SA plus SA plus SB plus SC. What's the largest I can make that sum subject to these constraints? And there are lots of problems. This is used a lot used a lot in industry to do production planning, for example. We're using it for a different purpose here to actually solve this network problem. So any optimization problem that is solvable in polynomial time can be solved in polynomial time by a linear program. This is an example. There are specialized algorithms for solving that workflow, but it's possible to solve it just using a linear program. So what was the idea behind this linear program that we wrote? First of all, what was the idea behind this diagram up here, this network flow problem? Where did it come from? What are we trying to solve for? Yeah.
I think we're trying to figure out how much oil can we get from S, which is like the starting point, to
T.
T.
Right. So the idea is, imagine S is sort of an oil field and T is a tanker port where oil is being shipped out. And you've got this network of pipes that you can move oil between nodes. And the question is, subject to the limit, so we can ship 4 units per hour from S to C. We can ship 5 units per hour from C to E, and so on. And we can put as much oil as possible, as much oil as we want to, into the pipeline beginning at S. And however much arrives at T, we can offload into the tankers. And so the question is, what's our maximum throughput we can get on this thing? Now clearly, you can't, for example, start by sending 3 units, sending the maximum amount of oil out on each pipeline. What would happen if you did that? What if you sent 3 units to A, 3 units to B, and 3 units to C? What would go wrong? Yeah. Okay. So if you sent 2 units from S to A, then you got a problem because A can only get rid of 2 units per hour. So we can't allow that. You can't send more in than is capable of being sent out. And you can't store anything at A. And the 3 units that go to B, at least 2 of them would have to be sent to A. So A would be seeing 5 units an hour. It can only ship out 2. So how do we express this in constraints? What did our variables stand for? Yeah.
Each one is an edge of the graph.
Each one corresponded to an edge in the graph. In particular, it corresponded to the amount of oil that's shipped over an edge. So SA stands for the amount of oil that we need to ship per hour from S to A. And DT stands for the amount of oil we should ship per hour from D to T. Okay, so we had to put constraints on that. So what did this first batch, it just basically says each variable is greater than or equal to 0. What did that mean? Yeah?
Oil can't go backwards. You can't
Okay.
have negative flow.
You can't have negative flow. The amount of oil that you send per hour has to be 0 or greater. So we're just saying that. What about this set in here that says SA is less than or equal to 3, SB is less than or equal to 3, SC is less than or equal to 4. Where did they come from? Yeah.
You can't, so for each edge, you can't send greater, it's like based on the weight of the edge.
Okay. So it's just saying SA less than or equal to 3. That's because the 3 is on the edge from S to A. You can't send more than 3 units per hour across that edge because the capacity is 3. You can't exceed the capacity of a pipe. So that's what the second batch of constraints says. And what about these equality constraints here that says, for example, SA plus BA equals AD? What does that say? Yeah.
Saying all of the edges coming into A equal the amount going out.
Right. That's has to equal the amount going out for each of the internal nodes. So for A, B, C, D, and E, the amount coming in has to equal the amount going out. So you see there we have these 5 constraints. Right? So what we're saying is, this characterizes what a legal solution is. A legal solution has no negative numbers. A legal solution never exceeds the capacity on any pipeline. And in any legal solution, the amount coming into an internal node is equal to the amount going out. So that's what all those constraints say. So subject to those constraints, we want to find the solution that maximizes something. And we're trying to get, essentially, we're trying to maximize the amount of oil that gets from S to T per hour. And there are 2 ways to express the amount of oil that's getting from S to T in an hour. What are those 2 ways? Yeah.
The max going out of S or the max coming into T.
Right, so either we need to maximize the amount going out of S, because anything that goes out of S will eventually make it to T, or we've got to maximize the amount coming into T. I chose to maximize the amount going out of S, but we can use a different objective, which would just be dt plus et, and we get the same solution. So the idea is a linear program. We describe all these constraints, we give the objective function we want to maximize or minimize, and then we feed it to our linear program solver, and it produces an answer for us. So what I'm trying to understand here is not how that solver works at the moment. I'm just trying to understand this linear program here. So lots of situations you could describe a linear program. So any questions about that? We're going to look at another example. But
How did the ones at the bottom make sure that there's only so much coming in and so much?
Okay, so it's asking about these down here. Let's look at this. SC plus DC equals CE. Okay, so here's C. So the edges coming in is this edge here, SC, and that edge there, DC. So in any solution, there'll be some number between 0 and 1 on this edge, and some number between 0 and 4 on this edge. And whatever it is, has to equal the number we saw for this edge, the amount F. Okay, any other questions? Yeah?
Let's talk about using this in industry. Before we can apply a linear program to it, the parameters would have to be done, because I can imagine a case where you have, like, if you replace the D with the 7, would you ever get a linear program that's not solved? You couldn't maximize it, just based on the design.
Could we have a pipeline for which there is no solution? I mean, you could have a pipeline for which it's impossible to get any oil from S to T, but I can't imagine one that.
Just by changing the weights of the edge, would you coming back to maximize it?
Yeah, I don't think so for this case.
Okay.
But I don't want to mislead you and imply this is how network flow problems are solved. There are specialized algorithms for network flow. When I say it's used in industry, the first couple of examples you looked at with figuring out the optimal amount of different kinds of chocolate to produce, that's more like it's used in practice. But for much more complicated problems, you're trying to optimize the use of, optimize a whole lot of things. Any other questions? Okay, so let's look at a different problem. Let's look at the shortest path problem that we solved using Dijkstra's algorithm, see what we can do. So here we have a graph, and I want to model the problem of finding the shortest path from A to every other vertex as a linear program, and see if we can solve it that way. And we describe the shortest path problem for this graph as a linear program. All right, now I'm going to give you something to think about. Suppose, I got a little problem with these directed edges. So imagine for a minute we've got a graph without the directed edges. It's just undirected edges. How could you find the shortest path from A to any other vertex in a graph with undirected edges? Forget about linear programming, forget about Dijkstra's algorithm. Tell me something physical you could do. A physical model you could make to solve the shortest path problem. for any pair of vertices. Like suppose you want to find the shortest path from A to B. How could you go to your workshop and build a physical model and solve the problem? Yeah.
Could you make a circuit where all those weights are resistances?
Okay, so you're talking about making a lift model,
Yeah.
and I'm going for something simple. Okay, so I think you could, but
Somehow stretch it out like a straight line.
okay, he said somehow stretch it out in a straight line. That's getting right at it. What kind of model would we need? Yeah.
Build a structure with like of where the edges are different lengths.
Okay. So imagine taking a piece of cord of length 2 feet, or 2 inches, a 4-inch cord, a 1-inch cord, and so on, leaving a little bit of extra for the knots we're about to tie. So you would tie the 5-inch cord and the 3-inch cord together, and that knot would be A. You would tie 3 cords together, and that would be B. You tie these 3 together, and that's C, and so on for B. The idea is after you've accounted for the knots, you've got 4 inches left or 2 inches left, and so on. So if you built that model of the graph, where the links between the knots corresponded to it has the same topography as a graph, links between the knots matched up with the numbers on these edges. How would you use that to find the shortest path from A to B? Yeah.
Hang it from vertex A.
Right. You can hang it from vertex A and pull down on vertex D. Pull them as far apart as you can until the edges go taut. And which edges would be taut when you did that? The shortest path. You would have the shortest path from A to D would be reflected in the taut lines. There would be some slack lines that wouldn't contribute to the solution. If you want to find the shortest path from any pair of vertices, you just pick those 2 knots and pull it taut. So for example, suppose you want the shortest path between C and B. Again, ignore the arrowhead because I don't know how to model that with cord. You take the knot for C, you take the knot for B and pull it tight. Okay? Which cord is tight? This one here. And these other cords would sort of be dangling down. Useless. You have found the shortest path from C to B is right here. So we're modeling, you can think of that almost as a linear program. How are the constraints expressed? In our physical model, what are the constraints? Yeah?
Just the length of the
Lengths of the cords. There's, the cords don't stretch. They can be pulled tight. So those are your constraints. And what's your objective function? What are you trying to maximize or minimize? Yeah.
Minimize the distance between 2.
Well, yeah, we're trying to minimize the distance, trying to find the shortest path. But are we really, when we do this physical thing, are we really minimizing anything? I'm trying to pull things as far apart as I can, am I not? So oddly, what we're describing is a set of constraints and then an objective, which is to pull, what's the furthest apart we can pull these 2 knots. So we find the shortest path by maximizing an objective, subject to some constraints. Because what if we tried to minimize it? Instead of solving it to see what's the farthest apart I can pull these to find our shortest path, what if I said, okay, what's the least amount I can compress them together? The answer would be 0 for everything, right? You could always make the 2 knots match up, and then everything would be hanging loose. So it's kind of a weird thing to think about, that you are trying to maximize something to find the shortest path. But it makes intuitive sense. It would work in practice. So can you figure out? Well, I'm not going to ask you to figure it out. I'll show you the answer, but I'm about to show you the linear programming equivalent of what we just talked about, the physical model. So I'm going to let A, remember we want the shortest distance between A and every other vertex. So I'm going to let A stand for the minimum distance from A to A. B stands for minimum distance from A to B, and so on. So we've got these 4 variables. Now, what constraints can you put on it? We're ultimately going to solve. We're going to solve simultaneously for all those answers, but what constraints can you put on it? Let's assume no negative edges. That's what Deich's algorithm assumes. What's a really easy constraint you put on each of these, given that I said there are no negative edges? They're all greater than or equal to 0. Okay? But there have to be other constraints we can put. We got to have constraints from the other side that keep these things from getting too large. What upper bounds can you put on these things?
Total distance.
Well, how do you express total distance?
A plus B plus C.
Well, that's what we're going to try to minimize. Or is it maximize? Yeah, we're going to try to maximize A plus B plus C plus D, subject to constraints. That's going to correspond to pull things tight. But that's our objective. What are our constraints here? All right, look at B. What constraint can you put on B? Yeah. Somehow these edge weights have to get into our constraints, right? Well, I think B has to be less than or equal to A plus 5. Whatever the minimum distance to A is, B has to be less than or equal to A plus 5. That's one constraint. What's another constraint we could put on B? Yeah?
B is less than or equal to C plus 1.
Yeah. B is less than or equal to C plus 1. There are only 2 ways to get to B. One is via A, one is via C. So we just say B is less than or equal to to C plus 1, and B is less than or equal to A plus 5. Okay. What about for D? What constraint could you put on D? The minimum distance to B has to be less than or equal to the minimum distance to B plus 2. There would be 2 constraints there as well. So, continuing in that vein, there's the thing we're going to maximize, and again, you might rebel and say, why are we trying to maximize A plus B plus C plus D? Because we're trying to find the minimum distance, but think about that physical analogy. And here are our constraints in addition to the one that says that they all must be greater than or equal to 0. So I said A equals 0 because we know that. There can't be a shorter path to A. There's no negative edges. And then those others, each one of those corresponds to an edge. So there's, except for A equals 0, everything else corresponds to one edge. And I've tried to motivate that before. The minimum distance to C can't be more than the minimum distance to D plus 4. It also can't be more than this minimum distance to A plus 3. So those are the 2 constraints for C. Okay, so you feed it in, and turns out that this is what you get out of the LP solver when you feed that program in. You find out that A is 0, B is 4, C is 3, D is 6. So it solves a problem for you there. So you can view this as a maximization problem. Model physically, you have to think about the way we talked about pulling the knots apart. So you can trick an LP solver into solving a shortest path problem. Yeah.
What's the complexity of solving?
To start over.
What's the complexity?
Oh. Okay, so there are at least three algorithms for solving linear programs. We'll talk about it more toward the end of class. But it can be solved. any linear program can be solved in polynomial time. I don't have a better answer than that. So better than exponential time. And in practice, they're just fast enough. Yeah?
If you just maximize one of them, like if you just maximize D, would you have still gotten the correct answer but only for D?
I'm not sure. That'd be something to try out, but I'm not set up to try it right now. You just said maximize B, subject to those constraints. No, I don't think you'd get the right answer. If you maximize B subject to those constraints, you'd get 5. It's important to have all of them in there so that you are simultaneously. Yeah. Any other questions? Okay, interesting fact is that for every linear program, there's a dual. And by dual, what I mean is this is a maximization problem. It is possible to mechanically, via an algorithm, transform a maximization problem into an equivalent minimization problem. And by equivalent, I mean if you solve the maximization problem and you solve the dual minimization problem, you get the same answer. And what we'll turn to next is look at how you do that, how you take a linear program and compute its dual. And then we will take this problem and compute its dual and come up with a really sort of a novel algorithm for solving the shortest path problem as a minimization problem. So let's take a break and we'll see how duals work. All right, let's get started again. Okay, so this is the program that we started with, the linear program, where we're trying to choose sort of a production strategy involving two boxes of two kinds of chocolate. Now, suppose you want to verify the answer. So, x1 and x2 are subject to these constraints. And we were trying to maximize x1 plus 6x2, which was sort of a profit. And this was given as a solution by LPSolve. Now, what if you didn't trust LPSolve completely? You wanted to just verify for yourself that it was correct. What could you verify about it? Yes?
You could test another couple solutions and see if they match more.
Okay. So you're talking about testing whether that really is the maximum. But what can we do short of that? What else has to be true about the solution for it to be valid? Yeah.
Plug x1 and x2 into all the constraints.
Right. So it's easy to check that these satisfy the constraints. These are at least valid in the sense that they're each greater than equal to 0, and that's these inequalities, and that's that inequality. And they do. It's trickier to verify that that really is the maximum. I mean, if your strategy was to sample, find other legal solutions, check whether the objective function exceeds 1900, you can do that for a while, but you're not going to get the result. So let's think about another way you could verify that the optimal solution really is optimal. Right? So those things are easy to check. So here's the observation. I see upper bounds right here. Upper bounds on x1, x2, and the sum of x1 plus x2. Let's experiment with just adding some together. So suppose I do that. So what have I done here? Yeah.
Substituting constraint for your objective.
Right, so my objective function was x1 plus 6 times x2 is well, that was my objective function. Well, here's my objective function, right? And I'm arguing that the objective function has to be less than or equal to 2000. How did I do that? Yeah?
By adding the constraint on x1 to 6 times the constraint on x2.
Right. So I have this constraint here. x1 is less than or equal to 200. It says so right there. It says so right there. And then I just sort of pull these coefficients out of my hat and simplify this. Ended up with x1 plus 6x2 is less than or equal to 2000, which I rearranged all the terms. So that tells us that this doesn't say you can get to 2000. It says that no answer can be greater than 2000. Now, can you pick different coefficients that would give us a tighter bound? Something different we could multiply those two constraints by, and then when we simplify, we end up with something better.
x1 plus x2 plus 5x2.
Okay, so we say add x1, x2, and well, let's see if it's the same as mine here. Is that what you said?
Yeah.
Okay. So we're taking this constraint that says x2 is less than or equal to 300, and we'll multiply that by 5. We'll take this constraint, multiply it by 1, and what if you want to use this to put an upper bound on the objective function? You can't just pick any old number. Why is it important? Why is use 5 important here as opposed to using 4? What's the art to this? Why wouldn't it serve our purpose to put a 4 here? When we're all done rearranging, we need to get our objective function less than or equal to some constant. So if we took 4 times this constraint plus 1 times this constraint, we would only have 5 x2s over here. And that doesn't do us any good. we need to come up with an inequality that says x1 plus 6x2 is less or equal to something. So if you pick 5 and 1, if you're lucky enough to pick 5 and 1, it works out, you get 6x2s and 1x1 must be less than or equal to 1900. And we're done. So just reasoning from these constraints, we're able to show that the objective function must be less than or equal to 1900. So you can't do that at 1900. So in principle, it's possible to prove the objective is that the solution is optimal. What's the problem you can see with doing that, especially as you get more and more variables and more constraints? What would it take to do? What did it take to do here? Yeah.
A lot more things that you'd have to do, and do a lot. It would take a lot longer.
Yeah, I mean, we're just sort of fooling around. I had 1 and 6, and that gave us a constraint, but wasn't as tight as we wanted. You know, then we found another way to combine these inequalities that gave us what we wanted. But as the constraints get more complicated and there are more of them, more variables, it's hard to see how to do this systematically, to actually take the program and figure just the right constraints to multiply, just the right constants to multiply these by, so you get an inequality with the objective on the left and the solution on the right. Yeah?
You could also visualize the objective function as a plane in space, that these constraints are restricting its domain.
Yeah.
And so if the paper's like slanted, the highest point on the paper is going to occur. Are these constraints like somewhere on the boundary? So like if you were to draw out these constraints on 2 space and find a corner, like and pick out all the corners and then just plug them into the objective function and see which one's the biggest.
Okay, so I think you're getting at where I'm going next. So let's go there and see if you agree. Okay. So we want to be able to derive those coefficients. So let's just, instead of multiplying by 1 and 6 or 5 and 1, let's just invent new variables and multiply by those and solve for the variables. Why not? So that's what I'll do. So I'll let y1 be the coefficient, and I'll multiply this by. And I'll let y2 be the coefficient, and multiply that by. So instead of picking specific coefficients, I just do y1, y2, and y3. And once I rearrange, I get this. I get y1 plus y3 times x1 plus, and so on. Okay, well that's good. But how can we solve those coefficients? Presumably, if we solve for these coefficients, we would get that y2 plus y3 is going to be 5, and where's the 400 one? Y3 is going to end up being 1, and the other is going to end up being 0. But how come in general, how can we solve these coefficients? How can we solve to figure out what values these variables should have so that we get the bound that we want? What properties these variables have to have? What do we want y1 plus y3 to be? Remember, we want this to end up looking like our objective function, which is x1 plus 6x2. So what do we want that to be? Right, we want y1 plus y3 to be, that's the only, we want y1 plus y3 to equal 1. And we want y2 plus y3 to equal 6. And what do we want for this to be when we're all done? Well, it'd be nice if that were 1900. But in general, we want this to be as small as possible, right? Because we're trying to put an upper bound on this objective function. So we want to have these things constrained in a certain way. We want y1 plus y3 to equal to 1. y2 plus y3 equals 6. And there are various ways to do that. We saw a couple ways up there. But we want to find a way that makes this as small as possible. So we've got some constraints on y, and we want to make that right-hand side as small as possible. How in the world can you do that? How can we minimize the right-hand side subject to the constraints imposed on the left-hand side? Has anyone ever heard of an algorithm that'll do that?
Is this a rhetorical question?
It is. It's just a linear program. So, here's our program. We're going to find, I've added in those constraints. We're going to find, we need to have y1 plus y3 equal 1, y2 plus y3 equals 6, such that that is minimized. That's just a linear program. And it's called the dual. So I told you before the break that you can take any of your linear program and turn it into its dual, where the solutions are the same. So the dual of a maximization problem is a minimization problem, and vice versa. So what we're doing here is deriving the dual program. So let's go on here. So this was our original program, and there's our new one. So there are our constraints, and here's our objective function. And there I've written it a different way. There's our objective function. There are our constraints. And traditionally, instead of writing these as equality constraints, we turn them into greater than or equal to. Since it's a minimization problem, that doesn't change the answer. And there's a solution you come up with. So if you feed this into LP solid, you end up with those coefficients. The important thing is they're the same. So any solution to a dynamic program, or any dynamic program, has within it all you need to prove that the solution is correct. The dual proves the primal and vice versa. Okay, so you can, there are tools that let you take a linear program and compute the dual, and they work like we just showed. You use the constraints of the primal. You emit some variables as coefficients. You come up with the program. So let's try doing that. Well, there's a duality theorem. Basically, if the primal has an answer, an optimal answer, then so does the dual. What happens when you compute the dual of the shortest path problem? So there's the primal, which is a maximization problem. And we are going to multiply by new variables. So for every constraint over there, I multiply the first constraint by u, the second one by v, and so on. So I've got u, v, w, x, y, and z. One variable for each constraint. I multiply 3 by those variables. I rearrange, so I get those constraints. That's just a little bit of algebra. I add and collect terms. And then what are my constraints? What are the constraints of my dual program going to be? What do we want to have u minus v minus x equal to? Remember, we want this, when we're done, to be the objective up there. So what do we want this to be? We want that to be 1. 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 And we want to minimize that. So, to make a long story short, here's your dual. So that is the dual to the program that we did before the break. It's a minimization problem, and when you solve it, you get that solution. And you get the same answer, 13, that you got out of the first one. The question becomes, is there any way to interpret the answer physically? In what sense is this giving you an answer? So in the dual, we can interpret the answer as saying, well, what we got out was the values of the variables were the was the distance from A to the corresponding vertex. What do the values of these variables mean in the answer? I'll draw you a picture. So there's our original graph, and there's our dual program. Here was the solution. And you remember, we used U to multiply the constraint that said A equals 0. And each of these other constraints, we used to multiply, each of these other variables, we used to multiply a constraint that corresponds to an edge. And I'll just show you which edges they correspond to. So the constraint for the edge this way to 3, we multiply by x. The constraint for the edge from B to D, we multiply by z. And here's our answer. It says U is 4. Remember, U is not on the picture. It was to multiply the constraint A equals 0. U is 4, B is 0, W is 2, X is 3, Y is 0, Z is 1. What do they mean? Yeah.
It's the reverse of the shortest path, so you would start at 4 and go in order the numbers.
Start at 4. How do you start at 4?
Okay, now I've got it.
Yeah, no.
I thought it was.
There's a simpler answer. Did anyone see it? I remember I computed this once, some years ago, maybe 5 years ago, and it took me a while, but when I discovered what those variables were telling me, I was blown away. It was like linear programming was computing an algorithm for me. Yeah.
And I'm just gonna to start like V and Y equals 0, and then
Okay.
take it. So it seems like it's kind of showing you like what edges are taken how many times. So
Okay.
X is taken.
That's exactly it. So what this says is, if you took this graph and you wrote the shortest path from A to B, what edges would it take?
X is the
You would go on this edge, it's labeled with X, and that edge is labeled with Y, right? So we use the edge from A to C once, we use the X edge once, and we use the W edge once in getting from A to B. Okay? What about the shortest path from A to C? You use the X edge once. And then the shortest path from A to D, you would use the X edge, the W edge, and the Z edge. This is just telling you how many times you use each edge for all the vertices. So you use the edge from B to D once, and that's to get from A to D. You use the edge from C to B twice. Once as getting from A to B, and once getting from A to D. You use the edge from A to C 3 times. Once in going from A to C, once in going from A to B, once in going from A to D. And this is just sort of an artifact up here. Think of it as the edge from A to A, or the root from A to A. You can use that on all 4 solutions. So that's the physical interpretation of these answers. And essentially you can use these, you can just sort of shade the edges and figure out the shortest path tree from it. It's telling you that these edges aren't used at all. You don't use that edge of weight 5 from A to B. You don't use this edge of weight 4 from B to C. The other edges are involved. So it's not always, I'm not always so lucky to be able to compute the dual and figure out how to interpret it physically, but in this case it is. All right, now I've been asked several times about the complexity of solving linear programming. So the simplex algorithm, it's the most famous, it was discovered in 1947. So, the first computers didn't exist until about 1946. So it was, it's a very early algorithm. In the worst case, it requires exponential time. But in the best, on practice, it works really well. So the exponential, the worst case doesn't occur in practice, at least not very often. In 1979, there was a Soviet scientist that discovered the ellipsoid algorithm. And it runs in polynomial time in the worst case, but it's bad in practice. So it's theoretically, it's an improvement over the simplex algorithm in that it doesn't require exponential time in the worst case. But it's not nearly as fast as simplex on average. So it's sort of like, you know, quicksort's twice as fast as merge sort, even though quicksort has a bad worst case. Right? And then there was a grad student at Berkeley in 1984 that discovered the interior point algorithm. It runs in polynomial time in the worst case, and it performs well in practice. And it turns out that the interior point algorithm and the simplex algorithm are still competitors to this day. They've sort of spurred improvements in each algorithm. So in practice, they're competitive with each other. I'm going to suggest to you how the simplex algorithm works. We're not going to go into great detail. So just remember the way we argued that the way I argued that the solution, the optimal solution, had to be at one of the vertices of the feasible region. So this is called the feasible region. So what do all the points in the feasible region of the linear program have in common? Why are they called the feasible region?
They're valid solutions too.
They satisfy the constraints. So the pink points here are the only ones that satisfy the constraints. And we want to find which of these pink points maximizes x plus 6y. And I argued last week that it has to be at one of the corners. And what was the crux of the argument? Well, what did this line represent? Okay, that's the objective function, and I picked, that's the line x plus 6y equals some constant. So I just picked some constant and drew this objective function. Okay? And as you increase that constant, the objective function moves up like this. Okay? And what's the last point? What's the last point when this line exits the equal region? All right, it's going to be up here. That's the last point. That point right there, where it's labeled 1900. That's where that line exits the feasible region. And at that point, the value of that line, the value of x plus 6y, the value objective, is going to be 1900. And that's the largest. And then it exits the region. So making x plus 6y larger and larger, moves the line up, and when it finally is at its maximum value before it exits the region, it touches that point. And why was it that it has to touch a point when it exits? What properties does the feasible region have? Yeah.
The max is always at a corner.
Well, we're trying to argue why the max is always at a corner. Yeah.
It's always a linear constraint, so you never have.
Okay. The line is always straight, it's not curved, because it's linear. And what about the edges here?
They're always straight lines.
They're straight lines, and furthermore, it's never concave. Okay? So that just means that when the line exits the region, it's going to be either touching a point or maybe touching a complete line segment, but that still includes a point. So that means you only got to look at points, at corners. And as there are more variables, we're talking about higher dimensional spaces, and we're talking about the corners of 10-dimensional solids or whatever, if they're 10 variables. The same idea applies. But here's another point, another fact. If you start at the origin, if in fact you start at any point, and you follow edges to the optimal, it's always non-decreasing. So you start at 0, it goes up to 200, up to 1400, up to 1900, and then it goes down when I go there. Or if I start here and I go 0 to 18 to 19, before it drops off to 14. So what does that tell you about how to solve the problem? How do you find the maximum? Yeah?
You start at 0, go to all the corners, and then wait till you decrease and go to
Yeah.
the decrease.
So start at 0. You don't even have to go to all the corners. You just start at 0 and you go to you follow some edge to a next corner. It doesn't matter. So we'll go to here. And then you look around and you find another corner. You find a corner that's bigger. I guess it matters. You need to go to a corner that's bigger. So you start here, you look for a bigger corner. They're both bigger, so we go here. We look around, there's a bigger corner. We look around, there's a bigger corner. Once we're there, we look around, there are no larger corners. So we're done. And the way to see that works is, when this line came up, what vertex did it hit first? There, which is the smallest. Keeps coming up, it hits that one, which is next. Then it hits this one, and then that one, and then that one. And no matter which way you go, this hill climbing algorithm works. You never get stuck. What you worry about is that you start somewhere, you follow the edges, and you get just to a local maximum, from which you have to decrease before you reach the real weather. But because of the geometry of this, that doesn't happen. You can just start somewhere, keep moving to an adjacent vertex that's larger, and you're guaranteed to get to the optimum. Yeah?
So how come that doesn't happen with the linear constraints? Or is that just with this example it doesn't happen?
No, it's an aspect of the linear constraints.
Okay.
But yeah, I don't think I could come up with a satisfactory explanation right now, but it just works out. Now the problem is, the reason that there's an exponential worst case running time is because there are situations where doing this hill climbing algorithm requires looking at an exponential number of vertices. And so the interior point method, which was an improvement, sort of takes shortcuts through the middle sometimes. Yeah?
So how does an exponential algorithm compete with a polynomial algorithm?
Well, an exponential algorithm is something of the form 2 to the n or 3 to the n or whatever. And for a large n, it doesn't compete at all. It just grinds to a halt. So we can put up with the exponential behavior of simplex simply because it doesn't tend to occur in practice, the worst case. Okay. And so, obviously there's a lot of engineering behind simplex to do all these geometric operations efficiently because you're working in high dimensional spaces. So I just want to tell you define a couple terms for you, and then we'll be done. So we've talked about feasible regions. So there are several types of feasible regions. First of all, there's a bounded feasible region, finite. That's what we've been looking at here. And in a finite, bounded optimal solution, the optimal solution is going to be one of the vertices. That's what we just argued. Okay? It's possible to have a feasible region that's empty. It's over-constrained. So this says x must be greater than or equal to 0, y must be greater than or equal to 0. If these say x and y must be less than negative numbers. So there's no points. The feasible region is empty. No solution at all. You can have an infinite feasible region. So this one, imagine the pink goes on up to infinity. We're trying to maximize x plus 6y. So that's an infinite feasible region, and there may or may not be an optimal solution. So why does this one not have an optimal solution?
One big x, y stays like
Right. X can increase without bound, and so you can always find a bigger x. But you can have an infinite region that does have an optimal solution. So here is an unbounded one that does have a solution. And why does it work? The same constraints. Did I say x can increase without bound? I should have said y can increase without bound. What's different about this one? Yeah?
You could just go to 0 and that's it.
Right. This is a minimization problem, not a maximization problem. And so the answer turns out to be at 0, 0. So if there's an answer, it will be at a vertex. But if the region is infinite, there's not guaranteed to be an optimum. In this case there is, the other case there wasn't. Maybe I rushed to get this all in because there's a question on the next assignment that I guess I didn't have to rush, it's only Tuesday, but anyway. It's good to know that for the next assignment. Not this week's, but last. Okay, we're done.